to be pretty good. I just said pretty good, why? First of all, you need to know that there's the vulnerability. You must be aware of it, okay? So you need some kind of disclosure, some kind of information about it. And also you have to make sure it's accurate enough. For this exploit, I saw some IPSs which has just one signature, which is iSystem activator binding request. So it's completely legitimate connection to this interface, RPC interface. And the fact that it says, oh, we're under attack. That's typically a huge false positive. Okay, and it's not going to be ever implemented. And then this attack is never going to be blocked. Exploit-based signatures. The interest with these signatures is that they can be completely done. Their purpose is usually to block, well, you know, those, outbreaking worms, mass-mailing worms, those major threats, which are very well known. You know, they're propagating, and you just want to protect your infrastructure from them. So here, you don't need an intelligent signature. Just going to see the payload, and this is the case here. I didn't provide the name of the vendor, because it's kind of shame. But anyway, the signature here for the DCRPC DECOM exploit, which is used in Blaster, is simply to, well, encode the name of the resource here. This is the resource that was called by the war. So the name of the server was something like, I don't remember, NXFB, something like this. Okay? So we're just looking for the name of the server which has been called. That's it. That's stupid. That's efficient against, well, dumb attacks, blind attacks. It's very efficient in terms of performances. You see here, stupid matching. But it's not going to provide any kind of security, or let's say advanced security. Very, very easy to bypass. So, let's make it clear. What I wanted to do, based on this story about signatures, is just to provide you a small example. I take this very old exploit, signed by everybody. Everybody, any IPS is supposed to block this very, very old attack. That's Blaster. How come you're not able to block it? So I take this exploit, okay, the very exploit, and then I just played a little bit with it. So just like changing the knob sled into increasing and decreasing the EDX register, okay, quite stupid obfuscation, why not? I changed some, well, exploit data, so like the name server we were talking about. And then I play a little bit with RPC features provided by the protocol. That's typical layer 7 protocol. I didn't add anything on it, on top of it, okay? So I do some fragmentation, pipelining. I just play with context alteration. I establish multiple contexts, and that's it. And just we'll see that we'll have to change just the port to remotely connect to get the shell. So from there, I used 3 different IPSs. One is not in line, and 2 others are vendors. I'm not going to name, not to get into troubles. And I launched the attack first. So you see they're all in a row. So this whole theory is saying that you need to use different technologies just to make sure that if you can bypass one, you will not bypass 2 of them. We'll see that here I'm able to bypass 3 of them. But let's start with the beginning. And here we see that we've got like, well, 6 different alerts which has been raised. First one, raised by Snort. It's just, okay, path overflow attempt, so typically the exploit. Then we've got something more generic, RPC DECOM interface buffer overflow and upsled detected by the second IPS. And the last one is generating 3 alerts. It was quite difficult to bypass it, I must admit. First of all, just a PDU which is quite large. Okay, maybe you can play with that. Buffer overflow on Microsoft DCRPC interface, and then the Windows command shell running this 666 port, which has been detected. So let's try to bypass them. First of all, if you want to play with Snort inline, it's pretty easy to bypass it because it's not able to handle multiple contexts. So in this small software, I just activate one feature, which is multiple binding. I say I'm going to establish, well, some sessions on some interfaces, interfaces, establish some bindings, and then bind on the iSystem activator and launch the exploit. So first it was just copy and paste from the code of Metasploit, and then I improved it a little bit more. We'll see why. But here it's very basic. It's not able to follow different contexts. So as my exploit is launched on a context which has context ID of, I don't know, maybe it's randoms, but not context ID 0, it's not going to be analyzed by Snort. So that's one. Let's try now to bypass the second one. Problem is the NOP sled. So as I told you, I just activate the obfuscated shellcode option, which simply changes, you know, this NOP sled into increase and decrease the register, and that's it. I bypass it. Pretty easy. Second one is an option I added, which is alt server, just to change the name of this NetBIOS resource. And we see that this IPS, for this signature, or this detection of RPC DCOM interface buffer overflow, we're just relying on the name of the resource. So kind of stupid and kind of very easy to bypass. Then we move to vendor number 2. The problem here is that, first of all, if I establish too much bindings, I'm not going to be able to reduce the size of the PDU, and I will still have this alert about overly large protocol data units. So I needed to edit a little bit the code, so I'm just establishing, when I ask for multi-binding, first of all, a binding on an existing interface, or I will raise an alert, and binding on iSystem activator interface. So it's just 2 bindings instead of something like 15 that we've got from the Metasploit code. And then I play with fragmentation at 2 layers. You see the frag size option is just playing with, well, the TCP data size. The 256 bytes, okay? Into this, I'm going to play with DC RPC fragmentation. This is the RPC frag size option. I'm going to generate, DC RPC packets, or data, of only 32 bytes long. It means that into a single TCP packet, I will have multiple DC RPC fragments. That's kind of pipelining. And here, where we'll see that I bypass all signatures, except one, of course, which is for the remote Windows command shell. So first, I tested with, you know, changing the port to like 23, because like Telnet, maybe it's not going to detect it. But of course, it detected that it's not Telnet opcodes. So I had another ID, and we see it's typical shortcoming. Just set remote port to 282, which is SSH. And here, no more alert. So we'll see why, but usually it's for performance issues. You want to save time, and you know that port 22 is SSH is encrypted, so you don't analyze it. And yep, you bypass it. So here you see that this very, very stupid exploit, well, not stupid, it was brilliant, but very old, with few minor changes. I'm not the king of reverse or whatever, so I just got the code and changed some stuff in it. I just played with a little bit of layer 7 features. That's features from the protocol. I did not invent them. And then I got it to work. I bypassed 3 IPSs in a row. And it's not all. I mean, we've been just playing a little bit with some layer 7 stuff, a little bit of fragmentation, payload encoding or whatever. But you've got all those representation tricks, which are very important for DC RPC, but all the, well, encoding you can find like in HTTP. And you've got this problem with the URLs. You know that, well, some basic evasion techniques, just encoding the URLs. But you've got some tricks. If you see the first one, you see that from the PHP BB, somewhere in the URL, I just double encoded the 2 Bs. So here, a signature analysis engine must be able to understand that here, in this kind of case, for this kind of signature, I must be able to decode and then to analyze. In some other cases, it's not I can do that. Okay, just try the other one, the other exploit. Okay, here you see that I did a double encode, the single quote and dot. This is part of the exploit. It's not something I did encode. The URL you're launching to exploit the vulnerability is written like this. So you need, or you should need, an engine which is able to know when to decode and normalize your URL and when not. And that's a problem. That's a problem in terms of performance, in terms of signatures, writing, time. That's a problem. So it was about signatures. We saw that a lot of weaknesses there, pretty easy to bypass, but it's not, or maybe there's even worse. It's hardware issues. So of course, that's the basement of your system. You know all those IPSs, which are running multi-gigabit, real-time, 100% security performance, and blah, blah, blah. Okay, so they're relying on the hardware. And this hardware, we wrote many kind of designs. We've got many kind of, well, devices or, well, chips we can use, like, well, generic CPUs, ASICs, network processors, and each and every of these kind of device have internal architecture and specificities. And we see that in some cases they will be good at performing some operations and very bad for some others. Also, you have a choice between just one component and then, well, distributed architecture with many components in different kind of architecture like pipelining, parallel, and so on. What is important is that you must understand that vendors know advantages and drawbacks of all of these. We know that some network processors are very good at handling small packets. Some others are very good at handling large payloads, but it's not the same. We know that with this ASIC, I will be able to do some regular expression. I will be able to speed up some NFA engine for regular expression, which is very good. Some others will hardly deal with some kind of encapsulation, etc., etc. Don't think that vendors are stupid. Just know that. I know that very well, okay? And then I think, once again, the most important is cost. Vendor knows. But come on, if I tell you I've got the best IPS, very good performances, any kind of packet, okay? But that's $1 million in the box. I'm going to say, no, come on, it's not possible. I've got to lower the price. And then I have, first of all, to make some choices and say I'm going to use this network processor. I know it's not good for this kind of operation, but good for this one. And this kind of ASIC, etc., etc. Also something important in cost. That's the acquisition of the chips. That's one thing. The second thing is basically the fact that you have to develop, maintain your software. That's high cost. So when you say, okay, I've got some kind of cheap ASICs, it's pretty good, but then in terms of development, it's a mess. Okay, each time you've got to debug, it's terrible. Then you say, okay, let's go on just one single CPU, Intel CPU, run on Linux. In terms of cost for development and maintenance, it's like nothing. That's something very important you have to keep in mind. So just quick reminder of, well, these components. CPU, okay, you know it, everybody knows. Very generic, low cost for acquisition and development. ASICs, dedicated to very specific tasks. So once again, vendors know what they choose this ASIC for, okay? If you program it properly for the proper function, it's going to go very fast, okay? But, well, it's kind of higher cost anyway. And then you've got network processors. Network processors are pretty tricky, you know? They're supposed to help you handle layer 3 and layer 4 operations. Like, and we're understanding like TCP, well, port session, all these generating cookies, etc., etc. But here you've got a lot of architectures which are different. And that's multi-core systems, but we'll see that. A lot of tricks. In terms of architecture, when an IPS vendor